Hi, good afternoon. Chittu, could you please let me know whether I am audible or not? Hi, Chittu, could you please confirm whether I am audible?
Yes, sir, you are audible.
Thanks, thanks. Okay, so let's start the session with week 9 content, which is switched reluctance machine, right? We have seen synchronous reluctance machine last week, and this week we will see switched reluctance machine. So, do you have any idea what are the differences between them?
Difference between switch reluctance motor and
Synchronous reluctance machine.
sir. Synchronous reluctance motor uses a permanent magnet. Am I right?
Uh, in synchronous reluctance machine, permanent magnet could be absent as well. Like where permanent magnet is placed, that is known as a permanent magnet assisted synchronous reluctance motor. Where permanent magnets are not there, that is known as simply synchronous reluctance machine. So
Yes, sir.
basically, permanent magnets are absent in both the topologies, synchronous reluctance machine as well as switch reluctance machine.
Yes, sir. In switch reluctance motor, the value of reluctance changes, right, sir?
In synchronous reluctance motor, value of reluctance changes.
No, in
That
switched reluctance motor.
in switch reluctance motor, value of inductance changes with rotor position. You are saying that is
Yes,
correct.
sir.
That is correct, and that is partially correct for synchronous reluctance motor as well. There also inductance changes, but it could be maintained constant with the help of distributed winding. But yeah, that is one difference between them. And those inductances are two important inductance is present in switch reluctance motor, which is aligned inductance and unaligned inductance. So unaligned inductance is where rotor tooth is aligned with a stator tooth and minimum reluctance path is there. So that is why aligned inductance is known as, uh, or rather it has maximum value, and unaligned inductance where rotor tooth does not, intersect the axis of a stator tooth. That is known as unaligned inductance, and there the value of inductance is minimum, right? Other than that, from drive circuit, you could observe that there is significant difference between these two motors. Like you need to supply different kind of supply to run switch reluctance motor. You need to do continuous switching. When your rotor starts rotating, you need to do continuous switching between the armature, so that once it is aligned with one tooth, then you have to switch off from the stator, then you have to switch on the next tooth, and so that your rotor pole or rotor tooth should be aligned to next tooth, so that force can be created and it should maintain its rotation. Okay. Any other difference? uh, Rajni, do you have any other difference, any other idea? I am asking here difference between synchronous reluctance motor and switch reluctance motor.
Hello.
Yeah, yeah, Rajni.
Uh, sorry, sir. I'm not that much aware of that one. Means,
Okay, okay, no problem. So, first, should we solve assignment problem or shall I show the basic geometry of switch reluctance motor? What would you guys prefer?
sir, first we'll complete the assignment thing, sir, and at last we can discuss means like.
Sure, if that suits you. Is it fine with you, Chitu?
Yes, sir. Okay, sir.
Okay.
No issues.
So, the first problem is a four-phase, eight-pole switched reluctance motor has six rotor teeth. Okay. Basically, it is 8 by 6 SRM. Okay. 8 stator tooth and 6 rotor teeth. Okay. So, we need to find the step angle
Okay.
for the speed of 1000 RPM. So, either you have to let me know the expression of a step angle or
Yes.
any other.
Step angle expression is there, na sir. It's a step angle equal to 2 pi by q into PR.
Exactly, exactly. So, a
It is in
step angle.
radians actually. Yes.
Yes, yes, it will be in radian. If you
Radians.
convert 2 pi into 360, that will be in degree. Okay,
Degrees.
yeah. So 2 pi by QPR,
Hmm.
where Q is what?
Number of phases,
And
Number
PR
of
is number of rotor poles.
rotor
no.
poles. Yes.
Okay, exactly. So 2 pi divided by number of phases is 4 into number of rotor poles is 6. So that much radian.
Sir, I have a doubt, sir.
Yes.
Sir, is the rotor teeth and the rotor face the same?
Actually, in SRM, all the phases or supply windings are placed on the stator only. Rotor has nothing but only iron pieces with certain structure. So if you haven't seen, so this is kind of rotor. So this is four pole of rotor. All are iron. Okay, all are iron, and here like that, you know, a stator is placed. My drawing is not matching, but ideally it should be like that. Here also it should be a minimum reluctance path. Okay, so that maximum flux will link, and this is known as aligned position, right? And why is it happening? Uh, Here the windings are placed. Okay, so if you curl your finger from dot to cross, there will be a stator MMF, a stator flux direction from top to bottom, isn't it?
Yes, sir.
Like that. Okay, so I haven't drawn accurately, but this is kind of a structure where all the armatures are placed here on the stator side. Okay, no any winding on the rotor. Okay, like that. So when this winding is on, it will also be on, and the stator MMF will flow accordingly. And if this rotor is slightly unaligned, if you see, let's suppose this rotor tooth is kind of here. Okay, when this supply is on, it will provide flux, and by the force, this pole should attract. Okay, and with this attractive force, this rotor tooth will align at this position. Okay. Now further, the next rotor teeth will be again partially at unaligned position, and now you give supply here. Okay, and yeah, this one, yeah. So if this is aligned, let's suppose, let me call it, one is aligned, okay, and two is now partially aligned or unaligned. So once number one is aligned, then there will not be any force on the rotor tooth number one. Now rotor tooth two, let us suppose it is not aligned. Okay, if certain position like this, let us suppose ki rotor two is at unaligned position. Why? Because here reluctance path is maximum, isn't it? Less iron path or air gap is higher because here let us suppose a coil is placed. So effective air gap is higher. This I hope you are able to visualize as slot, right?
Yes, sir.
Yeah. Now what is happening? This winding will be turned on. Which winding? This let us call as A. A winding will be turned on. Okay. Now because of this winding, this stator force will be produced in such a manner that this teeth will be attracted to rotor tooth number two will be attracted to a stator tooth number A. Okay. And hence this phenomena or this process is continuously repeated, switching off all the stator teeth corresponding to the unaligned position of the rotor teeth, and hence this entire rotation is maintained. Okay, so that was very basic. I explained very in really crude manner. Okay, so I hope you got the idea behind the operation of.
Yes, sir.
Yeah. So now you are clear that where is the phase on the rotor or the stator?
That is on the stator, no, sir. Phases on stator.
Exactly. So that's what Chitu asked at. What was your question, Chitu? Number of rotor poles is equal to phases, or what was the question? Could you please repeat?
Actually, here they gave number of rotor teeth, but the formula
Yes.
has number of rotor poles. So I asked whether the
Uh,
number of rotor poles are equal to number of rotor teeth.
exactly. Now you tell me, is it equal or unequal? Rotor, this teeth, all
Teeth.
teeth are creating rotor poles, isn't it?
Yes, sir.
Yeah. So now you tell me whether they are the same or different.
Same.
Same, exactly. So number of rotor teeth is equal to number of rotor poles. Number of stator teeth is also equal to number of stator poles. Okay, so in SRM, basically these two terms are used interchangeably. So please do not get confused about them, because in other machines they are not used as such, because there we use as number of slots or number of teeth. But here poles and teeth will be used interchangeably. Okay.
Yes, sir. Understood, sir.
Great. So now regarding step angle.
Sir, I got 11.255 degrees, sir.
11.255, right?
Degree cycle. It's a radians is 0.1963 radian.
Mm-hmm. Mm-hmm.
1 minute.
Uh,
What is it? Eight.
I think,
Okay, sorry, sir. Oh, I took some different value. 1 second.
yeah, it should be integral.
Oh,
We
yeah,
got
yeah. Sorry.
24 here and 360, so 15.
406. 0.261 is the radians.
0.26 is the radian.
Sir, I'm
261.
getting 15 degree. Is that correct?
Exactly, 15 degrees is correct. So 15 degrees is equal to 0.26 radian.
15 degrees, sir.
Yeah.
15.007.
Yeah, so 0.26 radian and 15 degrees is the correct answer. Okay. And what is the physical significance of a step angle?
Like for generating EMF, it will play important role as attraction, repulsion, means how much step angle it must be do.
Yes, yes. So like here we saw that how much step angle is required, how much it will move when any phase is turned on, right? So 2 pi by
Aligned
q,
and aligned, unaligned positions are there, no? So,
yeah. So 2 pi by q is the a number of phases, right, in that zone, and that is divided by one pole. So one pole, how much by a step it moves when any phase is given supply. So that is known as a step angle. That is why it has significance. Okay.
yes.
So that is all about this problem. Any doubt?
No, sir.
Okay, great,
Understood, sir.
great. So now the second problem is SRM with 6 stator poles. See again, here we are using a stator poles is equal to 6 stator teeth and 4 rotor poles has a stator pole arc is equal to 30 degree, rotor pole arc is equal to 32 degree. Okay, so rotor tooth has slightly higher arc or higher thickness compared to the stator, so that the aligned position should be maximized. And the aligned inductance is equal to 10.7 millihenry and unaligned inductance is equal to 1.5 millihenry. Okay.
Hmm.
Now we have to find out the instantaneous torque when rotor is 30 degree before the aligned position. Okay. So basically, that entire torque production is happening because of the positioning of alignment and unalignment, right? So a particular rotor position is given that it is 30 degree before the aligned position. Okay. At that rotor angle, how much torque will be produced? So torque is a function of rotor position. Do you know the equation of torque?
Yes, sir.
What is
Uh,
it?
that is 1/2 into I square into dl by d theta.
Exactly. So that is the torque equation. Half I squared dl by d
D
theta.
theta.
So here, if you are maintaining, DC current or kind of commutated DC current, then entire torque will depend on dl by d theta. How much is the dl by d theta? Okay.
Hmm.
Instantaneous torque we have to find at rotor is 30 degree before aligned position. And phase current is also given. Phase current is 7 amps. Okay. Now
Okay.
we have to find out the current. Can we find it?
Yes, sir.
Yeah. So important term is here to take care as dl by d theta. Or
That
to
is a
calculate.
slope, sir.
Exactly. That is
Slope. Slope equal to aligned position inductance minus unaligned position inductance by
yes
that
divided by
angle.
angle. Yeah.
Yes, sir.
Theta 2 minus theta 1.
Unaligned
So
position angle and aligned position angle. Maximum.
exactly. Yeah. So we have to find out the angle at aligned position and angle of unaligned
Unaligned
position.
position.
Yes. So here, this angle, we are not talking about instant of angle. We are talking about how much angle is aligned from the stator tooth to rotor tooth and how much angle is unaligned, because there will be some phases, right? Let us suppose from here, if rotor starts moving,
Mm.
okay, if rotor starts moving from here, now from here it is unaligned till the point it moves to
Nearer to the stator pole.
exactly. Now
Pole.
from this point onward, it will
Okay.
start aligning, right? So
Yes.
that will be in transition, and when it is aligned, let's suppose it is aligned, it starts aligning and complete alignment will happen at this angle, and even it will move, there will be partial alignment, so that we have to
Mm. Sir, unaligned position angle, I got 0.244 radians, sir.
oh excellent. So how did you calculate?
There is a formula for unaligned position theta 1, that is half into 2 pi by pi r minus
Uh-huh.
beta s plus beta r. Like
Exactly, yeah. Minus
already you
beta s.
no, sir, polar angle we have. So that polar
Yes,
angle convert into radians,
yes,
stator
yes.
angle plus rotor angle.
Excellent. So that is correct. So here again, the unaligned position is we have to take 360 divided by number of poles first, and after that we have to reduce the pole arc of a stator as well as pole arc of rotor, right?
Yes, sir.
So yeah, so you can see from this figure as well that this position is this is the pole arc of a stator, this is the pole arc of rotor. Okay, so we
Mm.
have to reduce from the overall one pole pitch in a what will be one pole pitch, that will be let us consider here from here to here, so that will be one pole pitch, isn't it? Now in one pole pitch there can be multiple alignment or unalignment. This figure looks messy, but please try to get it. Like these were the original poles, original rotor poles. Now, during this rotation from this number one to number two, this was number two, uh, the movement of rotor poles from number two to number one, there will be multiple stator tooth, right?
Yes, sir.
So we have to consider all those alignments, not only with one stator tooth. We have to consider all the teeth. So that is why we have to reduce the a stator tooth pole arc and a rotor tooth pole arc in between them, and it is how much? 8 by 6 SRM. So we have to reduce from that, and then we have to calculate, and from there only this expression has been derived. Okay. Any
Yes.
doubt yet till now?
No,
Sir,
sir.
could you explain again?
Okay,
I
from the
didn't
figure,
get slightly.
okay, okay. So let us suppose in simple, for simplicity, I am drawing, two status teeth and two rotor teeth.
Sir, both with the same numbers are allowed.
Not allowed, just for the explaining, I am doing it. Okay. Then alignment and unalignment will not exist, just
What
for
we
the
have done.
explanation. Yeah. Or 3 by 2 we can take. So, Chitu, did you get why same number of stator teeth and rotor teeth are not allowed?
Yes, sir.
Why?
Am I audible?
Yeah, you are
Hello?
audible. Yeah, you are audible.
Sir, what did you ask, sir?
Why same number of stator teeth and rotor teeth are not allowed in SRM?
Due to the magnetic locking, it won't get
Yeah,
demagnetized, sir.
no, due to locking, it won't move ahead until the next unaligned position will be there. Right. So once it is aligned, let's suppose uh, it was made like earlier. This position is locked, right? And no other poles are there. Only two stator poles and two rotor poles are there. Then once they are aligned, the strong magnetic locking are there. Now the next stator tooth should be available or next rotor pole should be available so that if the switching goes to the next phase, that should attract the rotor pole. And the switching should be off here so the stator MMF could be eliminated and the next phase should be turned on so that it should move to this position. Okay?
Yes, sir.
Yeah. Okay, like that. Here, uh, A and B. Okay. 1, 2, 3. Okay. Now, if the rotor is rotating from this position to this position, so how much is the right? So this much is the difference. This much is basically slot pitch. Okay. How much is the rotor pole pitch? That is nothing but this entire 180-degree is the rotor pole pitch, right? Now, uh, this rotor arc, if it has to rotate from this position to this position, let us consider the direction of rotation is anti-clockwise, and if it has to move from a stated tooth 2 to a stated tooth 3, it will have first how much will be the aligned angle. So aligned, right now we are talking about unaligned angle. So this expression we have wrote related to unaligned angle. So how much will be that much unaligned angle? So it will start from this position, okay, and it will go all the way to this position. And if we are considering 180 degree of rotor pole pitch, then again this position will be aligned. So we have to ignore this, and this position will be unaligned. So in one rotor pole pitch, how much degree is unaligned? That that span is considered as rotor pole pitch or theta one here. Okay, theta one, and this will be entire theta one. Okay, and to simplify that span, this equation is derived. First, you do 2 pi by number of rotor poles, so that will give you how much the electrical angle is occupied or mechanical angle is occupied by one rotor pole, and then from that you subtract the stator arc and rotor arc, and that will be your total unaligned position or unaligned span. So just now I showed here. So from here to here, so if you know eliminate this width and this width, the remaining width in a one pole pitch, this is one pole pitch, that will lead to your total span of unaligned position. So either you physically calculate from this position to this position minus this alignment and this alignment, you have to reduce from the this one pole pitch, or you can derive, which has been derived by the professor, or it is also given in the textbook, you can refer, you will end up with this particular equation. Okay, so anyway you can calculate both parts. Again, is it confusing? Shall I explain once more, or is it fine?
Got cleared, sir. Thank you, sir.
Oh, okay, thank you. So from this expression, let us go. Since we have expression, you can also try to derive at your own. Okay. So now it is half 2 pi by number of poles are 6. Okay. Minus a stator pole arc is 30 degree and rotor pole arc is 32 degree. So 30 degree plus 32 degree. So is it fine, or we have to convert into radian? I got your point, right?
Yeah, rotor
So
poles is 4 है ना?
rotor poles 4. Oh, sorry, exactly. Yeah, 6/4. Sorry, I am confused. 6/4.
And my question is directly we written angle directly in degrees, no?
Yeah, so we have to convert into radian,
Radian.
or you can convert this into degree, or you have to convert this into radian, whichever way is fine for you. Okay, so
Okay.
and just to simplify directly, if you want to calculate in degree, you can do like half. This one should be 360/4 minus 30 32, so 62.
62.
So it will be 190 minus 62. That should be 28 divided by 2, so 14 degree. So total
4.
14 degree is the span of unaligned position. Okay, and at this for this span, there will be minimum inductance that you will get. Okay,
Yes, sir.
right.
0.244 is the radians. Okay.
Yes, 0.244
44
radian.
radians.
Yeah, it's good to keep both the parameters, because here which value you'll have to plug in, radian or degree, because inductance has some finite value. So here you will need to plug in the value in radian, right?
Radians,
So that is
yes.
why it is good to keep both the values hand in hand. So now regarding a span of aligned position. So how much will be the span of aligned position?
That is theta 1 plus they given us an angle.
They have given this angle
Before align.
um,
30 degrees before the aligned position. They given us a 30.
Yes, yes. But at that instant, we have to calculate. Like,
Yes, I have to calculate. Yes, sure.
yeah.
That angle plus 30 degrees, if we add, then we can get no, sir. We can
That
reach aligned
angle.
position.
Okay, let us calculate. Theta 2.244 plus 30 degree into,
Degrees and 5 by 180.
yeah.
0.3.
So how much it will come out?
Sir, it's a 0.767 radians.
0.767, exactly. So this much is the, a span of aligned position. Right, so since we wanted to calculate torque 30 degree before the aligned position, that is why here 0.244 is the unaligned position, right?
Yes,
And
sir.
we are adding 30 degree so that it will be aligned after 30
Aligned
degree.
position after that, yes.
Yeah, so just for the same reason, we are directly using this technique and we are getting the span of aligned position. Okay?
Yes, sir.
Okay. So now we will plug in all those values, these two values, theta 2 and theta 1 in this expression of slope, right? So
Slope.
that we will get the value of dl by d theta. So the value of slope should be aligned and unaligned inductance values are given 10.7 minus 1.5, and this theta 2 is 0.767 and 0.244.
Sir, it is in
0.76.
millihenry, sir.
It
10
is
power
in,
you have to write, no?
yeah, it is in millihenry. 10 to
Millihenry.
the, yes, yeah, and 0.767 and here 0.244.
4.
So how much value you will get? Please
Sir,
let
it's a
me know.
0.0175, I got you.
0.05, 0.0175, right?
75. Yes, sir.
Yes, yeah. This is millihenry per radian, right? Or Henry per radian.
Henry per radian, sir. I converted into already
Yes.
Henry.
Okay. So T2, are you getting the same value?
Yes, sir. I got 17.59 millihenry, sir.
Right. So millihenry per radian. So now we will plug in the value of torque, which is half I squared dl by d theta. Phase current value is given 7 amps into 7 square into dl by d theta. We can plug in 0.0175. So you will have to calculate this value and the amount of torque you will get, that much should be the answer.
So 0.428 Newton meter.
0.428 Newton meter, that is correct answer. So any final question, any final doubt in this part?
Sir, you told one word now, sir. What is that? Spam? Spam or what is that, sir?
A span, like how much is it, spread over the phase. So a span, what I said, that how much is the spread between, how much is the distance between the rotor poles. rotor pole pitch, this angle, right? If you are calculating from here, so how much is the, this one is the distance or the span of the rotor pitch, right? And if you reduce the unaligned position from that, so after the calculation where you will reduce the unaligned position, you will get the aligned position, the span or distance in terms of degree or radian. Is it fine?
Yes, sir.
Okay. Yeah, so moving onwards to next problem. Okay, so here it is mentioned that total SRM of 8 by 6. First, the configuration is 8 by 6, right? 4 phase. If 8 slots of SRM is there or 8 stator poles is there, so basically it can make either 2 phase, 4 phase, isn't it? So kind of that. So you cannot make 3 phase out of it in SRM because it is concentrated winding. Now we have to, it is given that total MMF is 20% more than air gap MMF. Okay. And the length of air gap is given as 4 mm. Right. Now, the phase current is also given, and the number of total turns is also given. So, phase current I phase is 35 amps, and number of turns is 460. We have to find out the flux density in air gap. Okay, so I hope question is clear to you. Okay. So to calculate flux density in air gap, which parameter would be required from these much given data?
It's for area and
Hmm. Current is given, number of turns is given. Any relationship between MMF and flux density? So let me draw the magnetic equivalent circuit of it. So this is a supply, phase supply. So generally magnetic equivalent circuit is drawn for one pole. Okay. You might have seen in the lectures such kind of RSP1, RG1. So in one complete pole here you can see, like if you are completing one pole, so what will happen? This is like completion of one pole of flux lines. Okay. Now, how many air gaps it is facing? If it is aligned, let me draw an line, or have I? Yeah, this would be appropriate. If you need to draw the magnetic equivalent circuit, how will you draw? So, kind of. Okay, so
Three air gaps, na sir?
sorry, could you please repeat?
Three different type of materials is crossed. No, first it at the rotor part and a stator part. After that, it enter into the air.
Yes, yes,
After that, it went into the rotor part.
right, right. So this is the back iron, okay? A stator
Mm.
back iron or stator core, you can say. A stator back iron, a stator tooth, air gap, rotor tooth, then rotor back iron, then again this rotor tooth, and then again air gap, and then again a stator tooth. So all terms will come twice, okay? A stator poles or a stator tooth, rotor poles or rotor tooth, air gap will come twice, right? And then rotor back iron, okay? So in that fashion, you see it, the flux path, and then you can draw the magnetic equivalent circuit, which I'm going to draw you. Yeah. So this is a stator pole, okay? A stator pole after, because phases are placed in the slot, right? So this is the phase or where the supply is given. So this one is MMF after the stator pole, air gap. Then after that, there will be what? Rotor iron part. Why is it like that? I'll explain in a while when complete MSc is on. So this portion is for rotor back iron. These two are for rotor back iron, and after that, after flowing through the rotor back iron and rotor teeth, it will go to air gap again, RZ or RZ1 or R. Then again, it will cross the air gap and now go to the stator pole. Okay, now the stator back iron will also be covered twice, or basically flux will be divided in two directions like that. SY1, SY. Basically, one there is no need to write one because it is just denotion of one part or one pole we are drawing it for. Okay, so now in the flux lines you can see that a stator core is at out, and this rotor core, entire rotor tooth and rotor inner core, this entire area is inside. So from this flux lines also, you can see that this portion is inside after the air gap, and this stator core is outside of the air gap. That is why here this stator reluctance, stator back iron reluctance are considered as outer of the air gap. Okay, and this stator inner teeth or stator poles are just immediately after this air gap. So that is why they are connected in series of air gap. Okay. Any doubt here in this magnetic equivalent circuit of SRM?
No,
If
sir.
not, okay, great. Chitu, do you have any doubt?
No, sir.
Okay. If not, then now we need to find out the flux density in the air gap. To find out the flux density in the air gap, the critical thing from magnetic equivalent circuit or from the informations provided to this problem, which is MMF, right? Once we get the MMF, our aim should next aim should be to calculate the magnetic flux intensity, which is H value, which is dependent on number of turns and currents in the phase or slot. Right. Once you get the H, right, you can calculate magnetic flux density by a relation which is B is equal to mu H.
Mu H.
Exactly. So now to calculate H, what all we have to do, that is the next thing. Okay. So how can we calculate H?
Sir, HL is equal to Ni, sir. So H will be equal to Ni by L.
H will be equal to Ni by L. Okay, you are correct. But I would just like to partially correct you that here L will be which value? L you are referring to which value?
Length
Length
of
of
L,
the
air gap, sir.
length of air gap, right?
Yes,
And
sir.
since in this magnetic equivalent circuit you have seen that for one pole there will be two times it will cross the air gap, so you will have to take care of twice the length of air gap. Okay,
Yes, sir.
yeah. So let us move step by step. So first the number of turns per phase we have to calculate. Number of turns per phase will be how much? We are given with total number of turns as 460. This one is the total number of turns, 416. Divided by how many phases? Four phases. So how many number of turns per phase will be there?
460.
104, sir.
Yeah, 104 turns per phase. So this much turns are there in one phase. So how many mmf? How much is the mmf per phase?
Ni number of
Ni,
turns into current
exactly.
dial.
Number of turns per phase into currents per phase, right? So
3640.
104 into phase current is 35. So exactly it is 364
3640 ampere turns, sir.
ampere turns.
Yeah,
Okay.
yes.
Now we need to calculate H, which is ampere per meter. And this mmf is in a stator, right? On the phase. Now the mmf in air gap, there is one relation is given that total mmf is 20% more than air gap mmf. So mmf in the air gap could be 80% of whatever the mmf is here. Is it right to interpret like that, or total mmf is 20% more
More
to
than the
air gap? So okay, let us stator mmf is 1.2 times of air gap mmf. So air gap mmf will be a stator mmf divided by 1.2. So 1 divided by 1.2 is how much?
Sir,
0.83. Yes. Yeah, please.
uh, how is that 1.2 value is calculated, sir?
Oh, it is not calculated. Actually, it is mentioned in the problem that total mmf is 20% more than the air gap mmf.
20% means it is point 0.2, right, sir? You have
20,
written 1.2.
yeah, 20% more than air gap mmf. So, uh,
air
let's
gap
suppose,
emission plus 20% of that one. How to add?
yeah, so let's suppose you have 10 rupees and I have 12 rupees. So, I have 20% more money than you, right? So, in that sense,
Yes, sir. Understood, sir.
yeah. Yeah, so now it will be 0.83 stator mmf and stator mmf is 3640. So 0.83 into 3640, which will be
3021.2.
uh is it that or is it 3033.3?
3021.2, sir.
3021.2 you are getting.
Yes, sir.
Let 0.83 into 3640, 3021.2. 3021.2 ampere turns, still ampere turns. Okay. Now we have calculated air gap mmf. Now, what is the equation? Just now we discussed, right? How what is the expression in terms of h? H into
Which equal
12, right? mmf is equal to MF is nothing but HDL integration, isn't it? And
H
here
into
we can H into 2, right? So H2HL is equal to 3021.2. Now L is better written as LG, air gap. So H will be equal to 3021.2 divided by 2 into LG is 4 mm. Okay. So how much is the
3,77,650, sir.
3,77,650 okay. Ampere per meter, isn't it?
Yes.
Okay, so we have calculated H. Can we calculate B now? B in air gap is equal to,
Mu into H.
sorry, yeah,
Mu naught into mu r into H.
mu naught into mu r into H. But in air gap, anyway, mu r will be 1, so mu
No,
naught
yes,
into
sir.
H.
1. Mu r is 1. Mu naught equal 4.2 10 power minus 7.
Exactly. So how much is the flux density you are getting?
0.4745, sir.
0.4745 Tesla.
Yes.
Yeah, so this much value you will get in the air gap. Okay. Any doubt in this problem? Any final doubt? Okay, great. Then let us move to the next problem. So the data is given like that. SRM has a stator pole angle of 20 degree, which is also known as beta S is equal to 20 degree. Rotor pole angle beta R is equal to 22 degree. Okay.
Okay.
The rating of the motor is 400 RPM, 80 watt. Okay. And some parameters are also given, that efficiency constant. Efficiency constant is known as KE, right?
Yes, sir.
KE is given as 0.6. KD, duty constant. KD is given as 1. K1 is given as, just a second. So K1 is given as, K1 is 0.08. K2 is given as 0.75. A stack length to bore diameter ratio. Ratio, which is also known as K, is equal to 0.8. Okay. Magnetic loading, B is equal to 1.2 Tesla. electric loading A is equal to 25,000 ampere turns per meter. A stator outer diameter is 150 mm. So there would be one equation where these all constants must have been used to calculate output power relation, right? So according to that, we
Mhm.
need to calculate first part is calculate a stack length.
Sir, first we'll calculate diameter, sir.
You can calculate a stator bore diameter as well. So basically, we have to calculate three parts. So let me write it. What are all? So A
Okay.
is a stack length.
Mhm.
B is a stator bore diameter. C is a stator pole height. Okay, these three parameters we have to calculate. Okay, so first, please let me know the equation of that power, which is dependent on all the constant.
Output power equal to
Uh,
KE into
K into
KD into
KD into
K1 into
K1 into
K2 into
yes,
B into
B
D square into
D square into
electric loading. I forget, sir. You have to write electric loading also.
electric
Yeah.
loading
Into L into
L into
RPM speed.
NR RPM. Yes. Yeah. So this is the equation. So basically, it is similar as all other
Like
equations we have been using. Just that some constants have has been added up, like Ke, Kd, K1, K2. Other than that, this is electric loading, magnetic loading, and volume d square L into
yeah.
rotor speed,
Yes.
right? So
Yes.
because of geometry constraints and some other factors, some other changes in geometry and operation, these all factors have been added up here. Now, uh,
One more expression we can write, that is a stack length to bore diameter ratio, L by D ratio, 0.8 they
L,
given.
yeah, L by D they have given as 0.8.
0.8.
Yes.
Yes, sir.
Now, so here in L, if we plug in similarly, we have solved so many problems based on such kind of problems. But anyway, let us proceed. We should plug in here as L 0.8D.
Mm.
So P is equal to KE, KD, K1, K2, AB, uh, DQ, NR into zero point 0.8. Okay, so now DQ, if we have to calculate, or DQ, I think given, right? DQ is given, isn't it? A stator, no,
Outer
D,
diameter they given, sir.
they have
DS,
given outer diameter, right?
150 mm.
150 mm. So now we can calculate here DQ, isn't it?
Yes, sir.
P is P divided by K, KD, K1, K2, AB, NR 0.8. So which
Sir,
will be, yeah,
2.7007,
2.007,
2.7001
2.7001. Is it DQ?
into 10 power minus 4. And D is, sir,
Okay.
D is 64.63 mm, sir.
D is 4.63,
64.63 mm.
64.63 mm. Okay, so let us uh, first plug in all those values, then it would be easy to confirm.
Yes.
So KE is given as
Yeah.
KEKD is 0.6. So KEKD at once we can say 0.6 because KE is 1, KE is zero point 0.6 and KD is 1.
Mm.
Okay. K1,
Yes, sir.
K2 is 0.08, 0.75.
K1 is 0.08, K2 is 0.75.
0.75.
And A is 25,000,
25,000. B is
zero point 0.8,
zero point 0.8 and
and R
NR
is 400.
400. And power is also given, that is
80
80
watt.
watt.
80 watt.
B is 1.2, isn't it?
Now be 1.2, sir. Sorry, 1.2.
No, no.
Sir, K1 is 0.08, sir.
K1 is 0.08. K1 is 0. Oh, yeah, sorry. K1 is 0.08. Yes, thanks. K1 is 0.08. Yeah, power was 80 watt. So now, if we calculate, so now how much you are getting, you have to let me know.
Yes, sir. Once.
Yeah,
Sir, I'm getting 2.3148 into 10 power minus 4.
3148 into 10 to the power minus 4 mm cube, isn't it? This is d cube you have calculated.
Yes, sir.
Okay,
Sir,
yeah.
I got 60.82, sir. D.
60.82
82.
mm. Yeah, so that is correct. 60.8. This is also correct. Uh, I think if you take cube root of this value, you will get similar value, isn't it?
Yes, sir.
Yeah. So now, second part we have calculated, which is D. So we can calculate L also directly,
Yes.
80% of. So L is zero point 0.8 into 60.82 mm,
48.65, sir.
48.65 mm, exactly. Now the last part is a stator pole height.
So, for getting the pole height, we have to detect the yoke thickness, no, sir?
Yes,
We already know the OD, stator OD.
yeah. And
We
we also
already
know the rotor
diameter
OD.
of the rotor also.
Yeah. Basically, we know the bore diameter. So uh, first we have to find out the how much is the height of a stator, and
Mhm.
from that we have to reduce the stator yoke thickness or the stator back iron thickness, and then you can get the height of the stator pole. Okay, so let us go step by step.
Yes.
So how much is the stator height? A stator height is uh, a stator outer diameter. So a stator outer diameter minus a stator bore diameter. So a stator outer diameter is how much? 150,
150.
150 mm. And a stator bore diameter we have calculated 60.82 mm. Yes, so this will be 90, 89.18.
89.18, sir.
89.18 mm. Now, it is critical to convert it into, divided by 2 so that we will get exact stator height. Why? Because these are all in diameter, so we are considering both sides of the stator. So we have to divide it by 2.
Radius will get 44.59 one side.
44.59
59.
mm. So now this much is the stator height. Okay, this much is the which height from the geometry also you can see. This much is the 44.59 is the this much height. Now we have
Yes,
to subtract the value of back iron or yoke.
you
Yoke
think.
is this one. If you subtract this much, you will get the height of a stator pole. So how can we calculate this yoke thickness?
They already given us a stator pole angle.
A stator pole angle is 20 degree exactly. So we have to use that value.
How to use that one?
Right. So stator yoke thickness is beta s, which is d by 2. Why d by 2? You can also use r. So, mhm, a stator bore radius into this a stator pole angle.
Angle.
Okay, so if you multiply this pole angle into the radius of bore, so that much thickness is generally provided for the back iron thickness, and that is bore radius is bore diameter we have calculated 60.82, isn't it?
Yes.
So radius will be 30.41
4
into this angle is 20 degrees. So you will have to convert it into radian.
0.349 radius
0.349 radian.
is the
This
radians. The value
this
is 10.613.
10.61. So 10.61 mm.
Yes.
Yeah. So this much is the thickness of the back iron. Now, if you subtract this from this value, you will get your final answer, which is height of a stator pole. (44.59 minus 10.61). You will get how much? 33.98, I guess. Hmm? You calculate. I'll just take a 1 minute break.
Sir,
Okay. Yeah.
uh,
Yeah. Go
uh,
ahead.
uh, how I did is actually okay. Already we got the stator yoke thickness is 10.61, and we know the
Yes.
OD, that is the 150. Uh,
Yes.
150 minus that diameter 60.82.
150 minus. Okay. Yeah. Yeah.
150
150
minus
minus.
60.82 minus 2 into 10.613 by 2.
Okay. 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 Just let me write whatever you are saying.
Okay,
Okay.
same 33.977. Okay, sir. Got it.
Okay.
Yes. Yes, sir. Okay.
Just give me a minute. Okay.
Yes.
Thanks. Okay, so let us move to the next problem. Uh, 12 stators pole and 8 rotor pole, 12 by 8 SRM basically, three phase. We have to find out the ratio of rotor pole pitch to stroke angle. Okay, so basically we have to calculate both the parameters. So how much is the rotor pole pitch?
Pi d by p, sir.
Pi d by p, exactly. So rotor pole pitch, pi d by p. So pi into d. Uh, d is
No,
not given. Uh,
no, sir.
okay, so if d is not given, then we can calculate in terms of angle. Okay, rather calculating it in terms of exact because we are asked ratio.
360 by p, sir.
Yeah, so we can also calculate it in terms of ratio. So pi by in terms of angle, how much will be the pole pitch? So basically, entire rotor is spanned into 360 degree, isn't it?
Yes. Yes, sir.
So if there are n number of poles, so there will be 360 divided by n. That much will be the pole pitch angle.
Hmm.
So here, basically, the equation will become now 360 divided by number of poles. So that much
Yes.
is the rotor pole pitch angle.
45 degrees.
So here we
What?
have 8 poles, so 45 degree, 360 by 8, which will be 45 degree. Now, a stroke angle. What is a stroke angle?
Sir, stroke angle is 2 pi by number of phases into number of rotor poles.
Exactly. So 2 pi divided by number of phases into number of rotor poles.
Rotor poles.
Yeah. So basically, it is defined as the angle by which rotor moves in one electrical cycle in one phase. So how much it does move in one phase when one phase is being supplied from the stator in one electrical cycle. So basically, in one pole pitch, right? So it will be. It is better to convert into degrees. So 360 degree divided by number of phases is 3 into number of poles is 8.
Number of
Yeah,
8, sir.
yeah. It's not use the same
360
notation. So it will be 24,
15.
360 degree, 15 degree exactly. So now we can calculate the ratio. So ratio will be 45 divided by 15. So it will be 3. Okay,
Okay, sir.
great. So any doubt here, Chitu? Do you have any doubt in this?
No, sir. It is
Okay,
clear.
great. So let us move on to the next part. So 6 by 4 inner rotor SRM. Okay. Rated speed is 1800 RPM. Again, L by D is given as 0.7. So you know what you will have to calculate. You'll have to calculate the bore diameter. Okay, that is why this parameter is generally given. Now magnetic loading and electric loading is also given.
Okay.
What is B is 1.3 Tesla. Electric loading is 35,000 ampere turns per meter. Uh, Duty cycle is 1, so KD you can take as 1, and 80% efficiency of the machine. Okay, now K1, K2 also is given, so you know what you have to calculate. You will have to calculate power 0.68. So you need to calculate bore diameter, stack length. Okay,
Yes, sir.
that's all.
We will calculate.
Yeah.
Okay, they given efficiency, sir. Point.
This is written as efficiency, but I think you will have to use as KE, I guess.
Okay. Power.
Yeah, KE and KD. You'll have to use KD as you'll have to use as one, and efficiency is given 80%, and I think KE also is zero point 0.8 you can use. Okay.
Sir, efficiency is output power by input power.
Mm-hmm. Yeah, correct.
But here expression P out equal to we're having the expression. And
So,
we need one more parameter, na, sir, for calculating this.
which parameter you need?
Power input.
Power input you need.
If in case if not
Okay.
there, what is current is.
From power output you cannot calculate.
If we know power output, we can, expression is with power output only.
Yes. Power output is equal to K1, K2, Ke, Kd, d square L into A into B into rotor speed, right?
Yes, sir.
So all the parameters I can see here, isn't it?
L by T 0.7. L
See.
equal to point D. L value, D value also unknown, sir, but there is related. Okay, we can calculate from there. But we are
Hmm.
here. We have two unknowns. So D unknown, P unknown.
D unknown, P unknown.
Efficiency
Okay,
is
exactly, exactly.
0.8%.
I got your point. You are saying that output power itself is not given, right?
Yes, sir.
Uh, Let me see whether is it given or not. Yeah, it is given. Sorry about it. It is 15 kilowatt.
Oh,
Yeah, sorry. I did not write it. I thought I have written, but
yes.
okay. So L we will plug in as 0.7D. So we will get equation of D cube as power divided by K1, K2, and R into 0.7. 15,000. K1 is 0.0823, K2 is 0.68, K8.8, KD1 is 35,000, B is 1.3 Tesla, into rotor speed is 1800 RPM into 0.7. Okay. So how much are you getting DQ or D rather?
D cube is 5.844 into 10 power minus 3, sir.
Okay. And how much is the D? 5.84. 5.84 should be
Oh, so,
mm,
sir, I'm getting 180 mmd.
180 mm.
Hmm.
180 mm you are getting the value of D.
D. Oh, what?
That does not seem correct, but anyway,
One
we,
second, sir.
and even 5.84 into 10 to the power minus 3 also does not seem to be correct, Chitu. So
That is
I
also
think it's
180.
Sir,
DQ is also
180 only, sir. D is equal to
oh
180
okay 180 Then in the seed they might have not provided correctly. So anyway, you check it on your own after the session. So for the timing, I am writing 180 Okay.
Yes.
Yes, sir.
Yeah, 180 does make sense for such a high power. Yeah. Now L is 180 seems to be correct. But again, please check on your own. So L is equal to 70% of D. So it will be
126 sir.
126. Yeah. So this much only you need to calculate for all your assignments. One more thing what was left is yes, commutation frequency, isn't it? Commutation frequency you will be required to calculate in one of the problems. Commutation frequency, yes. So what is the commutation frequency? First,
NP,
yeah, what is the expression?
NP by 60, sir. Frequency
N NP by 60.
60.
Uh,
NP by 120 is there.
NP by 120.
120 of by P. NP by 120.
N into P you are saying, right? N into
Yes, sir.
P.
N into P. N into
N
P. P into number of poles.
right. So this is the correct, yeah. So this is the commutation frequency of SRM. Like how frequent you will have to switch the switching of the phases that has to be done, right? Because each time your rotor poles will move, then you'll have to switch it at high frequency. So for that purpose, this commutation frequency is calculated. So for this problem, how much will be that? 6 pole is 4 and speed is 1800 RPM. So let us calculate for this particular problem. 1800 into 4, 120. So 2, 3, 30, 15. So 60 hertz.
60 hertz.
Yes, sir.
So here commutation will be done with the frequency of 60 hertz. And so if you calculate time period, so 1 by
1 by
60,
frequency. 1 by.
yeah. So
It will repeat 0.0166 seconds every
exactly 0.0166 seconds.
seconds.
So each phase will conduct for this much time always. Okay, after that, next phase has to be turned on and the current phase has to be turned off.
Then
So
here,
that
NP by 120,
mhm,
number of poles,
number of poles is P, N is the speed
that
of
is,
the.
uh, sir, here poles means we have to take stator poles, no?
No, no, no. Poles means always rotor poles.
Okay, rotor poles, commutational frequency.
Yeah,
Okay, sir.
yeah, yeah. Though it is called a stator poles also, but it will be written explicitly that a stator poles.
Sir, poles are four,
Poles are 6 by 4 was it, right? 6 by 4, yes.
6 by 4. And I have one more question, sir.
Yes.
Normal expression, there is a one more expression that is a NP by 60. There, P is the pole pair.
P is the pole pair you are saying. Uh,
Mm,
no, the correct equation has only number of poles.
number of poles. Okay, sir. That one fine, sir. 120 up by P n equal to 120 up by P. One of the problem I saw, sir, problem actually.
Uh-huh.
In sir problem, they given NP by 60.
NP by 60. Then they
I
must have
tried
used pole
actually.
pairs.
Yeah. Actually, no, sir. They took normal poles. NP by 60 they took. Even here, there is no pole pairs, no.
Yes, yes.
There is north, south. Like we are.
Okay, you are talking in terms of permanent magnet poles, right?
Mm, yeah. In permanent magnets, it's a NP by 120.
Mm-hmm. Right.
And if it is a pole pair, then NP by 60 we used to take.
Yes, yes. So correct equation is NP by 120 only. 120
120.
by P. Yes. That
In one
that
of the a sir problem I found that is NP by 60 they took. And I have a question why they taken NP by 60. They see it's universally we know every time we use it to calculate N equal to 120 F by P. It's a fixed
right,
form.
right, right. Let me see the problem. Does it has options?
I know, sir, it don't have any option. Just they explore how to do the problem. There they took this formula and they put these values.
Hmm.
Values are different, not this one. Values are something different, but the formula what they used is F equal to NP by 60 they used.
Oh, and they took number of poles. So in the lecture problems you are referring to, right?
I'm telling, yes, sir, it is in lecture problem. Next week, what I will do, I will show that one. If, like, I
Sure,
will tell
sure.
you which one it is in, which video it is shown like that, which problem it is, problem number also.
Yeah. Or if you let me know the lecture number also, I could go there and see.
Actually, there is only three lectures are there, sir, in last week.
Yeah, 31, 32, 33. So first one, second
Uh,
one, or third one?
I think it's a second, sir, but uh, I'll tell you.
Uh, uh, or has he derived anywhere in between? Or you can refer any textbook. It is better not to refer the textbook to avoid confusion.
Okay, sir.
The best book would be by Bilgin Barker and Ali Madi book would be the best book. Otherwise, you can also refer Ramu Krishnan in anywhere, or you can search anywhere. You can verify from the text, the standard text. So
Okay,
they
sir.
would they would not lie. Means they would not confuse you much.
Uh,
Yeah.
okay, sir.
Okay. So any final question before closing this problem solving? So in the meanwhile, I'll present some model just to give you visualization about how the structure of SRM is. Chittu, do you have any problems? Any question? Any doubt?
No, sir.
Okay, so
Actually,
let
I
yeah.
feel this course little high for me, but still I'm able to understand it.
Yeah, great. Yeah, so honestly, this is a bit advanced course, and that is true. And this is not a generic course, but yeah, if you apply a little more effort, I think you will get it. And
Yes,
yeah, try to solve all the problems which has been covered in the lectures also,
yes, sir.
so that you will get more command and you will gain more understanding. So I hope you are following lectures thoroughly.
Yes,
Watch
sir.
lectures at least once or twice. Watch lectures. I I understand that there is not much explanation in lecture, but once you will, start following, you'll get the idea like how is it being derived and derive on yourself with yourself, like on pen and paper. So that would be better to,
Yes,
learn.
sir. Sir,
Yeah.
in lectures, I feel like it is like it is a completely theory.
Yeah, yeah, true. That is why in the end, I guess they have provided, problem solving.
Yes, sir. So I don't know how to start learning from this. Like it is full of theory. What should I learn from this? How should I start it? Like that, I get a bit confused.
Okay, so what you do, from my perspective, go to the problem solving, okay, and see if you are getting stuck there and on which topic you are getting stuck. Search it from the video. Where is it explained and on which slide it is explained. You see the expression, how has it been derived? You derive by yourself. And I hope that would be, efficient and quick way to get the idea of the topic. And from
Actually,
this, yeah,
so formulas are given directly, sir. There is no derivation like how we got that formulas. Like that is the thing we are facing actually. For example, say torque formula here, 1 by 2 into I square into dl by d theta. They just tell that this is a formula and how to get that formula. Like this is only one formula. Like there's so many formulas are there in that.
yeah, I understand. So for that, you'll have to refer text. One thing is that if you want to study in detail, so standard books are there for everything, every topic. So the only hurdle will be that for each week you'll have to refer one book. So there is not much time to cover all the topics in detail by yourself, right? So you just go, and nowadays there are many, chat GPT and all. You can search those topics, those derivations only is uh, specifically those derivations, so that you do not need to search every book. Like for SRM, you cannot read in 1 or 2 weeks entire SRM by textbook, or you have to solve assignments and you have also other jobs, right? So
Yes.
it would be better that important derivations only as quick as you can extract from anywhere, online, offline, any paper, any book. Just derive them, just learn how they have been derived. And any doubts are there, we can discuss in this weekly session, right? So that would be the effective way to, quickly learn what are the required for this course. I hope that should be useful, isn't it?
Yes, sir.
Yes, sir.
And after the course is completed, after you have learned the required, whatever is required for this course, then afterwards you can explore on your
Yes,
own.
sir.
For your interest, you can go after course, because such a short time you cannot pursue both in a great detail. So you have to focus on whatever has been covered in the course, solve all the problems, learn whatever has been derived, and that's in itself is a huge learning from my understanding. And after that, uh, based on your interest, because people do PhD in 1 or 2 machines, and here you will have to learn one machine every week. So there will be some compensation in depth and width of the knowledge, but again you'll have to adjust accordingly, I guess.
Yes, sir.
Yeah, so just quickly let me present my screen to show this. So are you able to see my screen? A
Yes,
magnetization
sir.
curve. Yeah.
Yes, sir.
So this you must have seen in the lecture if you have followed the lecture. So this is how with the rotor position this flux linkage varies, right?
Yes, sir.
So why the geometry? Let us discuss first. So this is the geometry. So how many stator and rotor poles are there? Can you please let me know?
There is a rotor poles are 4, sir.
Four. Yeah.
Poles are 6, sir.
Stator poles are six. So it is a six
For
by four
combination.
combination, right?
Yes, for combination.
And the power it is generating is 60 watt. So it is a 60 watt SRM with geometry of bow diameter is 80 and axial length is 90 mm. So in 3D,
Mm.
let me. So this is
90.
how this is how rotor poles are designed. So this is the protruded part, and this is how the stators are there. So you can see that at this particular instant, all the poles are partially aligned, isn't it?
Yes, sir.
Yeah, you can see that they are partially aligned. When they will rotate, they will either align or unalign. And winding, they have been winded like this fashion, concentrated winding. So in around a tooth, the winding has been done. Okay.
Sir, why you given, sir, here different in winding, in middle of winding, there is some separation you given. May I know why you
E-
given that separation? So slot liner will be there, that never be there, no? That type
Generally,
of,
yeah, generally they are not there, but it is provided, to have one insulation on the side. It is having in between, just to, uh, it is just a representation of that.
there
In
we can
actual,
use slot liner, no, sir? Slot liner.
here you are saying, no?
Slot, we are able to give the bobbin or something, no? So we use it to give slot liner.
Right, right. So it is a slot liner only.
It is in the definition. Sir, can you go to the definition? There, here. Pattern, this is the first one pattern. Second one is a definition. There, liner thickness is 0.25 and coil divider you can 2 mm.
Yeah, so it is a coil divider as 2 mm and liner thickness, if you see,
It's a
0.25. So
0.25.
this is the liner thickness, isn't it?
Yes, sir.
Yeah. So have you provided such kind of this
No,
divider
sir.
in?
No, no, I never. Actually, whenever I started some design, it will come divider. But what I used to do, I put a divider 0. But copper depth is instead of 100%, I go for the 95%.
Copper depth, you are saying?
Copper
Yeah,
depth, yes, sir. If you put 90, it will go little bit backside and yeah, 90, 9, not 59, 90, 90, 95,
95.
95, sir.
Yeah,
Little
like
wedge, like we
yeah,
can give something.
basically you are not covering till the entire air gap,
No,
I would
sir.
say.
No, no, it's not
Yeah,
possible actually.
yeah, it's not possible. And even if you provide some, tooth angle, then you can see visually that it is not going till that point. So here, tooth angle is not given at a stator
Even
pole.
if you give tooth angle also, we used to put 95 only, sir. For safe purpose, we used to put
Oh,
95. There is no any coil divider and slot fill is we go for the up to 0.5%.
okay. Okay, yeah. So in that way, you cannot cover entire 100%. Even then,
Mm, Never. It's not binding is very difficult, sir. But for small diameters, it's okay. We can do. When you go for the bigger diameters like 1.92 mm, it's very hard to do the winding. And there's a tension problem. Is that one winding we can do. When coming to second tooth winding, it will be like interference will come. Like it's very hard to do the winding with hand.
okay. And how much slot fill factor have you done?
45, sir. 45 is our like we cannot go above the 45. Never.
That is copper slot, not wire slot fill factor.
Copper slot will factor.
Copper
I used
slot.
to take American wire gauge. Actually, here we used to go for the wire gauge, 11.5
Okay,
like that. Here I used
right,
to
right.
gauge.
Which AWZ have you used? 23
Um,
or
we use it to more sure. This is depend on the different applications. So like it's a linear actuator different, and
okay.
it's a ignition coil is different. If it is magneto is different.
Hmm.
If it is a
correct.
traction motor, it's a totally different. That's why diameter is more.
Okay, right.
Heavy
So
duty
as
general, different.
yeah, so you can see as we are increasing the AWZ, our diameter is getting reduced. So for higher diameter, we have to go to the lower AWZ or
Yes,
SWZ, whatever.
yes, sir. And we'll take that coil divider. I never put actually. I used to see coil divider, but it's not there in real construction. No? So we never prefer.
Yeah. In even in my design also we haven't used coil divider, but
So if it
I
is
think
not,
I
why to use?
yeah I think
Because we have
ideally this is an ideal design where people must be using a stator divider. So it is
yes.
looking like this.
Slot liner
So
is sufficient, sir. Slot liner we can
yeah,
give 7, point
yes.
8. It is in definition. Yes, slot liner.
Slot
Liner
liner, how much have you kept generally? Point two is
point 0.6, 0.7, sir.
0.6, 0.7.
0.67. It's a depend on the mission. Like we use it to make
Like
6.6, 0.7.
for traction, how much have you kept?
0.7, sir.
0.7.
0.7.
So like that you can adjust from here.
And coil divided 0, sir. I use it with
Coil
coil divided.
dividers,
Yeah.
yeah, right. We can also increase the number of stands.
Mm.
So if I am taking 2 with 17, so slot fill factor is exceeding its limit.
Limit, yes.
Here it is not showing exceeding because here nothing is being done by hand. It is possible, but with very extreme
Manual, it is
socket
not possible. In it's coming to
manually
real
it
world,
will,
it's
yeah,
difficult.
right. 90.5, I think 80, 18, 18.5 should be possible. Yeah, this is possible. This does seem possible.
Mm.
0.45. Yeah,
Yeah.
copper slot, like further you can increase, but this is a typical values. So this is how we bind it. A linear view also you could see.
Mhm.
So this is how it is concentrated around a tooth, right? Now, here, I just wanted to show you, some graphs and first flux path, right? So this is how, it will rotate. I wanted to show you the aligned position. See, so here till this point, all the flux is flowing through, majority of the flux is flowing from this tooth to this tooth, okay?
Yeah.
And as it is getting aligned, you know, it is turning to zero because no force will be produced there. And now the next will be when it will, now this teeth is coming to aligned position slowly. So now you can see the green. Green is the higher flux density level. So here you could see that linkage is happening to this in accord this axis, isn't it? I hope you are able to see.
Yes.
Yeah. The increase, and now it is coming to completely aligned position, and it will go to zero, like close to zero. So now you can see the air gap flux density level also. So how much is it? 0.02, which is very small.
Mhm.
Where I'm showing at the left bottom corner, you can see B is equal to 0.021 Tesla. Are you able to see B is equal to 0.01021 Tesla at
Uh, okay, it's showing,
bottom
but it is not that much clear.
bottom left corner?
By color also we can guess, na, sir. Blue
Yeah,
color till
yeah,
color here
like
20.3 by
right.
7. 10 power
By
minus.
color you can guess,
Mhm.
but are you not able to see the left corner of the bottom side? Area
20,
you are able to see 61.85
22.
mm.
Yes, sir, it is visible, sir.
So B is visible 0.02.
0.02 Tesla, sir.
Yeah,
0.021 Tesla.
yeah.
Okay.
So from color you can guess. Another way to get exact value, you hover this cursor and you will see the value. And meanwhile you can see one which is fine for you, isn't it? Now let me rotate it further. Now it will further be reduced. So zero Tesla, almost zero linkage. Why? Because next phase is now conducting. Which phase? This phase. Okay, I'll increase further some angle. So now you can see here the flux density is 0.32 where alignment has been done. Rajni, are you able to see?
Value I'm unable to see, sir, but by using the color, I can guess actually. I can.
Oh, okay,
Yes.
okay. So here I am telling you the value. So here average value is 0.3 Tesla, but along the rest of the stator teeth near the air gap, it is still 0.0203, close to zero Tesla. Now further I am increasing the position and you can see the more it is going to aligned position, it is producing more flux density, isn't it? Now this entire region have the average of zero point 0.3 Tesla. And similarly, if you further increase, though I have simulated till this point, but if you further simulate, you will get much more floater position. So like this. So this is how basically flux lines look. What we were designing in the lecture. So this is how actually it is going from unaligned to aligned. So now still it is aligned here. 4, 5. Now it is starting to get completely aligned, and where torque will be 0 for that
More.
phase. So that phase will go to commutation off towards the off, right? And the next phase will turn on. And can you guess which one will be the next phase? Where the green you are seeing, right? See.
Yes,
So
sir.
this phase is getting turned off, and this phase will get
Green
turned
is
on. Yeah. So this phase was wound like this. Now this phase is wound like this. And now this phase is getting turned on. This is second phase. One phase, two phase,
mm,
three phase.
3.
Are you able to visualize it? One phase. This is one phase. Okay.
Yes,
This
sir.
is one phase. Now this is second phase, isn't it? And for second phase, how the alignment will happen? Like this. When second phase is getting turned on, you can see the dark green color means high flux linkage. So that is like torque will be produced much large compared at that rotor position especially. So that is how this graph is shown. So flux linkage. So this is the graph of flux linkage. So at this position, the flux linkage is maximum, and on the load, when you have provided load, so at this angle of 132 degree of angle, you will have the maximum flux linkage. So where the dark green color you are able to see at that instant, the maximum flux linkage will be there, and maximum flux linkage means maximum torque will be there. Not always, but for this condition. Okay, now phase two has now it's time to turn off the phase two. If it will rotate, and you see it is getting turned off immediately after, right? And now phase C will turn on because this rotor is at unaligned position. Phase C rotor, when the rotor will align to phase C is this one, right? Phase C is this one. Sorry, phase C is this one. And one rotor pole is completely aligned to pole B. So that is not going to produce any torque. Now the poles which are completely unaligned is these poles. Okay. And these poles will attract toward the phase C and see what happens. The linkage will start with phase C. Now phase C will turn on at this instant only. Okay. At this instant only phase C will turn on, and further the rotor will start rotating, flux linkage will increase, right? It will keep increase, it will become maximum here and then start reducing and go to the off position. Then again phase A will turn on. Okay. I hope you got the idea behind it. Okay. Any doubt here? Any question? So this is how continuous rotation will happen. This turn on turn off process that had to be done by your electronic switching, and it will keep rotating. And that is why so much switching is happening for each phases in one cycle. How many switching is happening? 3 times for 3 phases. So that is why you see this kind of profile is there in torque, which is not desirable. Turning off, then turning on, turning off, turning on, like this. That is why there is such a huge ripple. That is why SRM is known as very high noise producing device. How is the current waveform? Is kind of sinusoidal. You see. Sorry, sinusoidal I'm saying. Rectangular, square. One phase is on, one phase is getting turned on, the second phase is getting turned off, isn't it? And same thing will happen for the third phase. Okay. So at load condition, flux linkage profile changes, magnetization curve, flux linkage current. So these all information you will get if you delve deeper into the topic. But for basic understanding, I guess this much is sufficient. If you have any final question, please feel free to ask. Otherwise, we can wind up the session. Okay. Any final
Okay, sir.
question? Okay. So let us wind up the session. Thank you very much for joining.
Thank you, sir.
Have a great weekend. Thank you. Bye. Good night.
Bye. Good night, sir.